Our next talk is definitely going to bring some. Our next talk is on the latest hot topic in the cyber world, the Web3 security, the dark side of DeFi, how to spot potential vulnerabilities, which will be presented by the immunified triagers Rudra Singh and Arbaz Hussain. Please put your hands together for Rudra and Arbaz.
So hey everyone, it's very excited to be here, and today we will be presenting on Dark Side of DeFi. We're going to explore some of the potential security vulnerabilities we have in decentralized finance related to smart contracts and decentralized web applications in general. So who are we? I'm Arbaz, and I'm here with my colleague Rudra Pratap. And we both work as a smart contract triagers at Immunify. And we are very much interested in investigating this Ethereum virtual machine-based decentralized finance hacks. And previously, we have worked as an AppSec engineer in Web2 industry, and at the same time, we also create educational content, like we create community challenges based on the common vulnerability patterns, which is available at the GitHub. And we also post about the common postmortems we have, bug fix reviews of the bugs on Medium, at Immunify Medium. So agenda of the talk is we're going to explore what are the smart contracts and decentralized finance in general. Then we're going to compare this Web 2 and Web 3 architecture flow, like how they differ from each other. We're going to look into the common decentralized application vulnerabilities related to the web. Then going to look the most common smart contract vulnerabilities. And outro, we have this slide where we have collected some good resources to get you started with smart contract hacking. So what are these smart contracts? So smart contracts are basically, they are just regular program code, and they contain sets of instructions and conditions that needs to be executed. The only difference the smart contract has is they are immutable. So what it is mean by immutable is once they are deployed on a decentralized network like blockchain, their state can't be modified. So they are immutable in nature, and they are deployed on multiple different blockchains, such as there is Ethereum, Solana, and Polkadot. Like many of you are familiar with different blockchains. And they are very widely written in very high-level languages like Solidity, which is very much inspired from JavaScript syntax. Then we have this Viper, which is another language in which this code is written, which is highly inspired from Python syntax. Then we have this classic Rust and a stack-based programming language, which communicates with virtual machine. So all these languages contains a set of opcodes, which is operational codes, which helps in communicating with Ethereum virtual machine to store, read, and execute instructions. So we're going to now do a very basic architecture comparison between the Web 2 and Web 3. So in Web 2, like if a user has to access a web application, he goes to the browser, he enters the application name, and the front end tries to communicate with the back end, and the back end tries to fetches the information from the database. And the database renders the information directly at the front end level. So this is the general Web 2 architecture flow, but things are slightly different when it comes to Web 3 architecture flow. So in case of Web 3, when you go and enter a decentralized application URL, the browser try to load the application, and the front end directly try to communicates with the smart contracts which are deployed on blockchain. So browsers does not have ability to directly communicate with the smart contracts or a blockchain, so they use a middleman here. And the middlemans are the wallets, which basically helps in communicating, transferring out the information from the blockchain to the front end. So this is the general architecture workflow difference between Web 2 and Web 3. Now, like many of you guys have seen, might have seen this MetaMask or a Wallet Connect, like wallets, but what they are basically. So wallets helps you create a digital identity on a blockchain. So what I mean by digital identity is they create your own account on a blockchain. And using that account, like you can store the digital assets like Ethereum, it could be like any USDT token or ERC7, like NFT assets and all. And whenever you create a wallet, it creates two pair of keys. The first one is the private key, and the second one is the public key. So private key basically act as your master key because it gives you an access to the wallet. So using the private key, you can access to your wallet, your digital identity. And there is a second, which is public key, which basically represents your address. So if I need to send you some Ether, or if I need to communicate with you, you must share your public key with me. So it basically represents your identity address. And wallets, as we have discussed in our previous slides, they handles all the communication between the smart contracts and a front end, like read, write, execute functions on a smart contract, which is deployed on a blockchain. So now we are going to do a basic authentication comparison with a Web 2 and how it differs with a Web 3. So in Web 2, we used to have, like in order to authenticate, either we need to provide an email or a password, or we might need to use some auth providers like Google identity or Facebook identity, like login with Facebook, login with Google. But in Web 3, like the authentication happens based on the signatures. Like in the GIF, you can see there is a login with MetaMask button. When you click on it, it generates a message. And once you sign that message, you are basically logged in as, you are basically authenticated. And the whole process happens in the background is based on the signatures. So why signatures? So, and what are these signatures? So signatures are basically 65 bytes long hexadecimal string, and it is produced with your wallet. So why signatures? Because as we have previously discussed, that when you create a wallet, it generates you two pair of keys, that is private key and a public key, and you can't use private key to log in into the application because due to the sensitivity in nature, and it gives you an access to your account. So signatures are basically produced with the wallets, and they are meant to be public. And the whole purpose of the signatures is to prove the ownership of an account. So if I say that if I own that particular address, then I can produce a signature and I can give it to you, and you can just verify if the signature belongs to me or not. So one of the use case of these signatures was to do an offline gasless transfer. So whenever you wanted to do a transaction on Ethereum, like whenever you wanted to send out some tokens to some other user, you must pay a gas fee. But using this signature, it solves that problem because you can just create an offline signature and you can pass that signature to some other user. And he can use that signature to just do an transfer behalf of you because you just verified the signature. So now we have seen that GIF in the last slide where authentication happens. So let's look at the workflow behind the workflow. So whenever user initiates a login, it sends the request to the backend, and it asks the backend to generate a random nonce. And once the backend generates the random nonce, the user, that message is get combined with the nonce, and the user signs that message. And once user signs that message with the wallet, it produces the signature. And signature is sent back to the backend, and backend uses that signature and try to recover the address from the signature and validates if that particular user is actually the owner of that address. And once it validates, it generates the auth token. Like auth token can be like JWT token, and once you have this auth token, you are fully authenticated. And the last thing the backend does is a cleanup process, which basically making sure to expire the nonce which we use, so that each unique nonce is produced for each login iteration. So here's an example of auth workflow. So this is a simple HTTP request, which makes post-based request to generate JWT endpoint. and it has three post data values. The first one is the address, which is your public digital identity address. And second one is the 65 bytes long signature, which was you just produced by signing the message you have that I'm signing my one-time nonce 2619. You sign that message and it produced that signature. And the request goes to that endpoint, and the endpoint try to validate if the signature is the correct one. And once it verifies, it generates you the JWT out token. So now we're going to look at these common authentication vulnerabilities, which will be discussed by Rudra. So he can take over.
Hi, everyone. So in the further slides, we'll discuss about what are nonce and signature replay attacks. And later on, we'll learn about a common misconfiguration in dApps, which can lead to authentication bypass. Missing random nonce. So the question would be like, what is nonce? Nonce is nothing but a random unique value, which is generally used as a separator to create a unique signature. So whenever we request it, it helps us to create a unique signature. And these signatures are generally meant to be used once. So if an application is failing to invalidate the signature, then there are chances that the application might be vulnerable to signature replay attacks. So in the given figure, you can see that there is an endpoint called generate JWT. So it takes three components mainly, which is address, which is the address of the signer who is signing the message. The signature is nothing but the message hashed with the public key of the signer. And the message is the message itself. So as you can see, I have highlighted that the message value does not have any unique element to it, which is nonce, of course. So there is no nonce. So whenever we try to create the signature out of this message, then the resulting signature would be the same. It is because there is no unique element attached to it. So the resulting signature would be the same, as there is nothing unique to it. So it's recommended that we add random nonce so that the signature cannot be replayed. Moving forward. Validator arbitrarily accepts any message. So as I said, we'll take an example of the same. So an application is said to be vulnerable to these kinds of attack if the backend of the application is failing to validate whether the user provided message and the signature is something that the application asked for. So it's not that we are arbitrarily providing some gibberish in the message or the signature. So let's understand it further with the help of an example. So I'm not sure whether you are able to see the figure or not. So it's of Etherscan, which have this huge data set of public verified signatures. And as Arbaz mentioned, that signatures are meant to be public. It's not sensitive in nature. So if you have noticed that this is one of the entries of the database, and it consists of address, signed message, and signature, which is the same required by the application. And generally, for authentication in Web3, these are the only three components. Generally, there are more components, but mainly these three components are used for authentication purposes. And what if we just replace an arbitrary, random entry from Ethereum database with our endpoint that generate JWT based on the three components? So when we send it to the server just generally takes the signature and try to recover the public address out of it. And in this case, it would be the address of the signer that we took from the entry itself, because it's a valid signature at the end of the day, right? Then there are chances that we can generate JWT token of an arbitrary entry from Ethereum database. So how can we prevent it? So generally, applications need to verify that the signature provided us by the end user and the message itself is something that the application asked for. So we are not arbitrarily providing any random gibberish. Client-side injections. So as you know, that XSS is not unique. Web2 has XSS, but it'll go like P2, P3, or something like that. But in Web3, the case is totally different. We consider as P1, critical. But the question would be why? Why do we consider? Because as you may know, that there are extensions installed in browser, which are namely MetaMask. So when we try to visit any dApp, they inject their native code so that we can interact with the application and the MetaMask extension. So injecting any arbitrary JavaScript code on an application would allow us to initiate a false or a fake transaction in the origin of the website that we have injected. So it allows us to create or initiate malicious transaction. So the same case happens with BadgerDAO, which allowed the hacker to steal assets worth over 120 million. So what was the incident was the hackers was able to find out 0-day in Cloudflare, which allowed him to inject arbitrary code, JavaScript code, on the client side of BadgerDAO. And so the hacker did nothing, but they replaced the client side code that would initiate transaction from the user wallet to the attacker wallet, leading to the loss of 120 million. Arbaz?
So we have just seen the common decentralized application authenticated vulnerabilities. Now we're going to jump dive into decentralized finance and common smart contract vulnerabilities. So decentralized finance, so it's the same, it has the same concept like the traditional financial ecosystem, but it was created using the blockchain technology. So users can buy, sell assets and perform exchanges and like borrow, take out the loan on a decentralized finance, but the only difference is they are not centralized and there is no middleman in it. So some of the examples is decentralized exchange, which basically allows anyone to come and trade exchange like exchange swaps. Like you don't have to go and create an account, like you don't have to do any kind of KYC. So that's the like plus point they offer. And there is like borrowing lending platform where users can come and supply some asset X as collateral and can borrow Y asset. And yield farming protocols, like whenever you have some tokens lying idle in your wallet, you can just invest into yield farming protocols and generate and fixed interest on it, like similar to the traditional finance we have. Then we have this derivatives, which is basically related to the futures, calls, and options. So it has all the same concepts. It was all produced using a blockchain technology in a decentralized way. Now, let's look at the common smart contract vulnerabilities. So we have 3 cases, which is very common, commonly spotted vulnerabilities. The first one is unsafe external call. So what are the risks associated when you force a contract to make an external call to some untrusted contract? What could go wrong? Then secondly, we have this griefing vulnerability where griefing basically means the attacker has no profit motive. He does it like to create a disruptions of service, like denial of service, like DOS. And the second, and the last one, we have this insecure external dependency, like what could go wrong if smart contracts are relying on some output value of a third-party contract and doing something with that value. We're going to explore one by one case. So first, let's understand what are these external calls. So external calls are basically every smart contract communicates with another one by making an external calls. But here are some risks associated with it, like when you force a contract to make a call to some untrusted and third-party contract, like what could go wrong? As smart contract could be it's not in a state where it could handle such outcome reaction of the callback. So we're going to explore what are the risks in the next slides. So basically, there are 2 types of external calls the smart contract makes. The first one is the static call, and the second one is the delegate call. So they both allow us to call some other function of a contract. The only difference is the static calls allows you to transfer out the ether as a balance to some other contract. So let's understand the first vulnerability, which is a commonly found, which is a re-entrancy vulnerability, and it's been done with a call method. So re-entrancy occurs when a function makes an external call to some untrusted third-party contract, and you use that third-party contract to make a recursive callback to the original caller contract. So you are just making the callback to from where the incoming call has come. And it does to steal funds or do some malicious activities. So we're going to explore one with this example. But first, who can be the callers? So there are only two callers who can actually call to the smart contract. The first one is the EOA, which is us, who are not smart contracts. And the second one is smart contracts itself. So smart contract can call other smart contracts. So let's understand with a small snippet about this attack vector. So there is a withdraw balance function. And the first thing it does is when you call this withdraw balance function, it tries to retrieve your user balances. Like message.sender is the one who is calling that function. So it try to fetches the amount of balance you are holding, and it try to store that balance into amount to withdraw variable. And on the next line, you can see message.sender.call. So it's making a call method to whoever calling this function. And basically, it's saying to transfer out the funds, like whatever the funds we just save in amount to withdraw variable. And third condition, we are just checking if the transfer was success or not. If it not, then the function will revert. And lastly, we are updating the state. We are updating the balance. So we are just keeping user balances message.sender to 0. So firstly, we are trying to retrieve balance, then we are transferring out the balance, then we are just setting the balance to 0. So what could go wrong into it? So let's say there is a simple exploit contract which has this receiving incoming call function, where we are just checking if the call coming from the vulnerable contract, then again try to call back to withdraw balance function. So what happens here is when message.sender.call, it will basically try to call this function, and this function will again execute this withdraw balance function. So the whole vulnerability here is the amount to withdraw variable. We just try to fetches the balance, and it's stored into that balance, and it try to send that balance. But at the last line, we are just updating the balance. So it will assume that the user has the same balance. So it keeps sending the balance again and again until it until the whole contract is drained out. So how to fix this vulnerability? Like you can able to like re-enter into the same function. So there are two popular ways the projects have been doing. The first one is the mutex locking. This is the same concept like thread processes use, so that they don't modify each other's state. So they just lock the state so that another process cannot access that state. And the second one is checks effect interaction pattern. This is a popular pattern which many experienced developers follow. So in this pattern, the first condition is we need to perform checks, then we need to perform effects, then we need to do lastly interaction, any kind of interaction to external contract. So let's see this pattern into more detail. So here's the comparison with vulnerable pattern and the checks effect interaction pattern. So you can spot that in the vulnerable pattern, we are doing interaction first, then we are updating the state at the last, setting the balance to 0 after transferring out the balance. But checks effect interaction pattern first try to fetches your balance, it stores into amount to withdraw variable, then it updates your balance to 0. Then it does an interaction to the third-party contract, so that users, even if they try to re-enter, their balance is already set to 0, so they can't withdraw more than once. Now let's look at another call method, delegate call, and let's understand this delegate call with an example. So the call and delegate call, they both use to call some other function of another contract. The only difference with the delegate call is, let's suppose there is a contract A and a contract B, and contract A is making a delegate call to contract B. So contract B has this set num5 function, and when contract A makes a delegate call to contract B, it executes that set num5 function in a contract B, but the storage happens at the contract A. So if we look at the memory slot, like if we look at the contract A slots, it end up updating storing the value of phi in contract A, not our contract B. So it's just executing the logic of contract B while updating the state of contract A. So that's the only difference it has. And using this method, like contract A can preserve states, like it can use any logic, but the storage will keep getting updated. So it can be used, this method can be used for preserving the storage. And this whole delegate concept introduced the concept of proxies. So smart contracts has this proxies contract, which we are going to explore now. So the proxy, basically the whole functionality of the proxy contract, it is used to just storage. And whenever you make a call to proxy contract, delegate call, it just forwards your delegate call to the logic contract. And the logic contract basically executes your logic, and all the state changes happens, and the balance update happens at the proxy contract, not at the logic contract. So there are two types of proxies. The first one, like they are the popular one. The first one is transparent proxy pattern, and the second one is universal upgradable proxy standard. The only difference is you can upgrade the logic contract, like whom you should forward the call. You can upgrade the logic from the proxy itself, and the second one is you can upgrade the logic contract from the logic contract itself. And there is a popular vulnerability associated with these proxies that is like very simple to find, and it's related to uninitialized proxy bugs. So every contract which is related to proxy has this initialize function, which is basically saying, like once your contract is deployed, you wanted to set some things like some variables, some access control roles, or whatever. So initialize function has ability to do that, and that function is only callable once. So once you call that function, you can't call again. So that's the use case of this initialize function, and a lot of times it's not a problem. Like keeping initialize function public, it's not a problem because they don't contain much problematic. But problem will occur when they have this logic where when you call this initialize, and whoever calling the initialize, it will grant a ownership to that. And once you become the owner, you can upgrade the contract itself. So that's very harmful. And like once a user get the upgradability, he can just destroy the contract itself, or he could drive the contract into some unstable state, which could make the proxy contract useless. So let's understand this whole concept with a diagram. So there are these users who are calling to this proxy contract, and the proxy contract just making a delegate call to logic contract. So it's just forwarding all the calls to the logic contract, and whatever the executions happens in the logic contract, it updates the state in the proxy contract. So this is the normal workflow. Now let's suppose there is a malicious hacker who just found a way where he can use the logic contract to make an external delegate call to some malicious contract which he deployed. And that malicious evil contract contains a special EVM opcode which is self-destruct, which is basically saying to destroy it itself. Like whoever call that opcode, it will destroy the contract on the blockchain. So he forced the logic contract to call the evil contract which he deployed, and logic contract executes this instruction, and all the state changes happens in the logic contract, not in the evil contract. So now when users try to call the proxy contract, the proxy trying to forward all the calls to the logic contract, but it is destroyed already. It's not, since the attacker already forwarded the call to self-destruct and it's deployed. So the proxy becomes useless as its storage and code are erased from the blockchain. So there is a popular bug which was found in Wormhole. It's related to the same. So there is initialize function where when you call the initialize, there is a ownable init condition, like which basically means you make the caller as the owner. Like whoever call this function, it makes the owner. And once you become the owner, you can authorize upgrade your logic contract. So the white hat found the bug in a wormhole where there were like 1.8 billions of assets were residing. And he can hold the entire contract for a ransom. And he reported through Immunify, and he got a bounty of 10 million for his findings. And we also created a POC for reproducing all these bug in a local environment. So do check out that POC. Now, coming up the next vulnerability pattern, which is push versus pull pattern, which is very commonly found. So will be discussed by Rudra.
So a push versus pull pattern. So generally, this class of vulnerability happens when a smart contract is trying to send ethers to a user, which could be us or a smart contract. So the result of this, the exploitation of this class would lead to griefing. So griefing is nothing, just basically in layman's term, you can say that we are just destroying the logic or making the smart contract unable to be usable by other users. So let's discuss with the help of an example. Let's suppose there is an NFT auction workflow. So the workflow of the NFT auction works as follows. So there is a smart contract called NFT auctions, which is residing in blockchain. So it's user one is making a bid of, let's say, suppose NFT for an NFT, and he's bidding $100 for the NFT itself. But at the same time, user B overruns him, and he or she makes a bid of $200, and like smart contract will think the $200 is much bigger than 100. So let's return the money back to user one because he just lost the bid. So this is the general overflow. The smart contract is returning the money that the user one sent at the initial stage and refunding it. So this logic looks like something like the snippet that we have shared, and you can find it on our community challenge GitHub. So the code says nothing, but it's just saying that if you lost the bet, just the smart contract will return the money that it is owned by the smart contract. So how can we exploit it? So let's suppose we deployed a evil contract, and we are making a bid of $100, and at the same time, someone outruns us, and while returning the money, we just break the logic. How? We implemented a fallback function in our smart contract, which just says that if someone sends me the money, I won't accept it. Just return or just reject the money. So we are destroying the logic of the contract. So when the NFT auctions try to refund the money, we are just saying we won't accept it, and it just reverts. So making the NFT contract unusable because it won't process the transaction and it won't move further. So NFT that the user 2 won would get lost. It's just stuck in the smart contract, and it's not unable for anyone to use further. So the fix for the same would be like using the pull method. So the major differentiation between the both is that instead of sending the transaction at the same logic, instead the user one requests for the refund. So we have created another function. So it just says that give me my money back, and that's it. Like it's a simple explanation to pull.
So the third and most common vulnerability case we see in a DeFi is a spot price dependency. Like we're going to explore what more in the spot price. We already mentioned that in order to determine some price of an asset, like any token and all, the smart contracts must rely on some source of information. And what could go wrong if that source of information could be manipulated or could return a very stale data? So price oracles. Let's understand the price oracles before we jump into the spot price. So price oracles are the smart contracts which basically determines the value of an asset. Like if I wanted to identify the value of Solana token, I can go to Oracle and I can just, it will just let me know like how much it will cost me to buy an Solana token. And like in order to develop such like price identifying contracts, like we can't really rely on like APIs. Like if I have to develop an application in a Web 2, I can just go and rely on some API endpoints of like Coinbase, some very good sources of like CoinMarketCap, CoinGecko. But things are very different when it comes to blockchain. Like you can't integrate an API. You have to always rely on the blockchain data, like on-chain data, like decentralized exchanges which are on blockchain, like Uniswap and a balancer. And in the next slide, we're going to see how the spot price calculation happens in a blockchain. So let's say I wanted to buy 1 Bitcoin and I'm holding Ethereum. So I can just go to this Uniswap decentralized exchange and I can look into the ETH and Bitcoin pool. And the way it calculates that how much Ethereum it will cost for me to buy 1 Bitcoin is basically by grabbing the reserve balance and dividing by them two. So let's say the pool has 20 Bitcoins and the another asset is it has 100 Ethereum. So we just divide y by x, which is 100 divided by 20, and it says that to buy 1 Bitcoin, it will cost me like 5 Ethereum. So now, like one thing we can understand from this is how the price, how much it would require for me to buy is how much is dependent on the amount of tokens residing in that pool, like the amount of reserves. So it's really easy to move the price based on making buying and a selling pressure. So mainly the attackers take out a lot of loans and manipulate these reserves, and whoever relying on these reserves, they will go and exploit there. So we're going to in the next slide, I have a figure where we're going to explore how this vulnerability can be exploited on a borrowing platform. So this is a normal borrowing lending platform where user have to deposit some X assets as a collateral, and they can borrow Y assets, and they can just pay interest of borrowing asset and can get back the original collateral which they supplied. So there is a user which has 1 Ethereum, and he goes to the protocol, which is a vault protocol, and he says, I'm going to deposit 1 Ethereum, and I wanted to borrow like 900 USDT, or like give me all the USDT of whatever I am depositing. So now the vault, what it tries to do, it tries to find the value of asset you just deposit, like it deposit 1 Ethereum. So it try to find the price of 1 Ethereum you just deposited. So when it query the price of 1 Ethereum, it goes to the Uniswap, the same pool which in the previous slide we discussed how price was calculated, and that pool will return the price is $1,000. And the vault now says, yes, the value of your deposited collateral is $1,000, so you can borrow up to 900. That's your limit because all the loans are under collaterals. So now let's look at another case where attacker simply has like $10,000, and he can directly go to the Oracle pool of Uniswap, and he can just swap, he can just sell his $10,000 of USDT, and he can just try to buy all the like majority of Ethereum from that pool. So what happens when you make a large transaction like this? It will push the price of Ethereum, like it inflates the price of Ethereum in the decentralized exchange. And once the price is inflated, the attacker can supply the 8 Ethereum which he got from the first transaction, and he can supply that 8 Ethereum to the vault, and the now vault try to query the price. Like vault again goes to the Oracle and say like, can you determine the price of assets the attacker is depositing, and now the Oracle returns the $10,000, which basically the inflated price, the last traded price of the Oracle, and the vault says that you just supplied the 8 Ethereum, like you can borrow up to 72K worth of USDT. So The attacker just risks 10K USDT to manipulate the pool, and he borrowed 72K. So it's like 62K profit for an attacker. He can just run away by manipulating and exploiting the vault. So this is a very common bugs we see around in DeFi, where oracle manipulation happens and someone goes and exploit the vaults and runs away. Yep, so what are the solutions to this spot price? The many protocols follows on time-weighted average price. They follow, so instead of depending on the last traded price, they have this time ranges like 30 minutes, 60 minutes interval, and they just averages all the fluctuations happens between. So they follow one, and the second one, the method they do is instead of just relying on one source, they rely on multiple sources. So they just combine all the other decentralized exchanges, and they just combine up, and they get an average price. So that's the way they do. And that's it. Like, that's all the common vulnerabilities we have discussed about the decentralized applications and about the smart contracts. So in this slide, we have collected some useful resources to get you started with blockchain hacking. And yep, that's it. So due to the time limit, we could not able to do QA, so we will be around. So if you guys have any questions, feel free to reach out. Thank you.
Thank you, Rudra and Arbaz. Like, definitely Web3 is so attractive. As you people mentioned, like, every bug is P1, and who doesn't want that money? Thank you so much again for sharing all the knowledge with us.